Hey folks, welcome to Chapter 4, Section 3. We're going to be looking at intermolecular forces of attraction in a compound, and this is Part 1. So let's look at where we've come so far. So now we know molecular formula, right? And from a molecular formula of a covalent compound, we can draw a Lewis structure. From the Lewis structure, we can determine molecular shape. From molecular shape, we can determine polarity. From polarity, we can now get to intermolecular forces. These are the forces between molecules. And I've provided some examples here of a polar and a nonpolar molecule, right? Of going from molecular formula, H2O, drawing the Lewis structure, where we have 4 electron domains, 2 bonding, 2 non-bonding. That gives us a bent shape with 109.5 degrees-ish between the atoms. And we have polar bonds due to the electronegativity differences, and we have a polar molecule. And then we will determine molecular forces. We have CH4, which we can draw as this Lewis structure. In 3 dimensions, it has tetrahedral shape, 4 bonds around the carbon, and all those 4 bonds are identical in a symmetrical geometry, so it is nonpolar, and there will be certain types of intermolecular forces there. All right, so at the end of this lecture, I'll give you some molecular formulas and ask you to do each of these steps with it. Okay, so let's talk about forces of attraction and intramolecular and intermolecular. We're going to be focusing on intermolecular. Intra always means within. So intramolecular are forces of attraction within a molecule. The forces of attraction within a molecule are what we call covalent bonds. Okay, that's actually the things we've been talking about before are within molecules. But intermolecular are forces of attraction between molecules. And we're going to focus on talking about liquid and solid states. If you recall, the way we talked about gas states are that the molecules and gas particles do not interact. So there are no forces of attraction between gas molecules. So we're talking about liquids and solids here. And when it comes to the strength of these forces of attraction, intramolecular forces are much stronger than intermolecular forces. So bonds, right, within a molecule are stronger than the attractive forces between molecules. It turns out the intermolecular forces are approximately 5 to 10% as strong as covalent bonds. So they're much, much weaker forces, but they are important forces. The intermolecular forces of attraction between molecules determine the physical properties of a compound, like boiling point, melting point, solubility, how much of it will dissolve in water, things like that. So why and how do we have intermolecular forces? Well, this is one of the core concepts. Intermolecular forces of attraction occur between the partial charge on one molecule and the opposite partial charge on another molecule. Right, so remember we talked before about electron distribution and unequal pulling and sharing of the electrons, and that can lead to partial charges. Well, opposite charges attract, and so if there are 2 molecules nearby, one has a positive end and one has a negative end, the 2 molecules will align themselves so that those 2 ends are pointing towards each other, and there will be an attractive force between them. We will spend the next few slides showcasing that phenomenon and trying to make some more sense of it. There are 3 types of these intermolecular forces, which depend on the polarity of the molecules. The first is dispersion. The second is dipole-dipole. And the third is hydrogen bonding. It's not really a bond, it's an intermolecular force, but we call it hydrogen bonding. But just remember, it's not really a bond. Okay, so let's look at dispersion forces first. These are sometimes also called London forces or even van der Waals forces. And dispersion forces are found in all compounds. Nonpolar, polar, it doesn't matter. All compounds can do this, but mostly we're going to be thinking about nonpolar molecules um, having dispersion forces. That'd be molecules that do not have a molecular dipole. There are no partial charges within the molecule. This is, in effect, the weakest intermolecular force of attraction. So let's walk through how nonpolar molecules can lead to intermolecular forces. And we're going to use the figure down here at the bottom as we discuss it. So imagine we have a bunch of nonpolar molecules all around each other. And as we see here, the electrons, even though they're evenly distributed, they will naturally shift within the compound. So as the electrons are, moving around and shifting, what can create is a temporary dipole. This is called an induced dipole, where at a moment in time, a partial positive and partial negative part of the compound will appear. It will be temporary and induced by just the general natural fluctuations of electron density. But once this is formed, now the molecules around it will be impacted by this induced dipole. So this weak attraction between temporary dipole and its next door neighbor will induce a dipole there. And say, well, here there's a positive charge that will pull the electron density here slightly towards it, creating an induced dipole here. And the ripple effect, essentially, is that one induced dipole will create more induced dipoles, which will then flow through the molecules. Okay, and this induced dipole in neighboring molecules will produce an attractive force between them. It's weak. It will be shifting and moving. It's not going to be a very strong attractive force, but it is there. Okay, and so this is something that we need to consider when we're thinking about intermolecular forces. Nonpolar molecules only have access to dispersion forces. And there's another factor about the molecule that plays into the strength of dispersion forces, and that is molecular size. So compounds with larger molecules have stronger dispersion forces than compounds with smaller molecules. For example, propane, which is CH3H8, has stronger intermolecular forces than methane, which is CH4. So the smaller molecules cannot produce as strong of an induced dipole and have weaker forces between them. The same is true for elements. Elements that have larger atoms have stronger dispersion forces. The electron density has more room to flow around back and forth and can produce a induced dipole easier. So for example, iodine I2, the molecule iodine, would have stronger intermolecular forces than molecular fluorine, F2, because iodine is larger. Okay, so the bigger the molecule, it has stronger dispersion forces. Now this is nonpolar. If we have polar molecules, they have access to permanent dipoles, and those permanent dipoles will interact to give dipole-dipole forces. So these are formed by polar molecules, and they are stronger than dispersion forces. Here's a way to think about it. We have formaldehyde here as an example, so CH2O, which has a permanent dipole indicated by the arrow here, right, pointing towards the oxygen. And a schematic way of drawing this is just simply as kind of like, it's almost like a magnet with a plus and a minus side. So this is a simplified way of drawing it. And I just realized that it's actually flipped, right? The minus side should be towards the oxygen. There'd be a partial negative here and a partial positive at the bottom, but that's okay. We get the idea of what it would look like as a schematic of the formaldehyde molecule. So then when a many number of formaldehyde molecules are around each other, they will align themselves in such a way that the plus and negatives are next to each other. So the oppositely charged ends of polar molecules are attracted to each other because they're between permanent dipoles. They are called dipole-dipole forces, and they are stronger than dispersion forces. Now the third type is what we called hydrogen bonding, and this is really just a special set of polar molecules that have the strongest dipoles. If you remember the trends of electronegativity in the periodic table, F, O, and N have the largest, highest electronegativities. And so when they form bonds with hydrogen, that will be a very polar bond. So there's going to be a very strong partial negative on the fluorine, oxygen, or nitrogen side, and a strong partial positive on the hydrogen side. So any time that we have an HF, HO, or HN bond in a molecule, there will be hydrogen bond intermolecular forces between these molecules. And these are indicated with a dashed arrow, right? And it's the same kind of idea that the plus lines itself up with the negative of another, and then there's going to be a strong attractive force between these because it's such a polar bond. It's a really strong, it's essentially a strong dipole-dipole, but it's kind of in its own category because it's so unique. Water is a great example of hydrogen bonding forces, and water is a very small molecule, but it's unique because of its strong hydrogen bonds. And you can see almost like a lattice structure here of how H2O molecules align themselves. If we kind of pay attention, here's one water molecule, here's another, here's another, right? And so they will line themselves up basically so that the H's are each pointing to the O's, and the O's are pointing to the H's, and it's still going to be tetrahedral shape. So the hydrogens, which have a partial positive, will be attracted to this lone pair of electrons here. Okay, and a reminder that it's not really a bond. We just call it hydrogen bonding. And it's a special type of dipole-dipole interaction between partial positive pole of H and the partial negative pole of F, O, or N. So only F, H, F, O, or sorry, H, F, H, O, or H, N form hydrogen bonds. So I made a little nested diagram here to think about intermolecular forces. So dispersion forces is the largest category. All molecules have dispersion forces. And then a subset of those, which would be just polar molecules, have dipole-dipole intermolecular forces. And then a subset of those, which are the strongest bond dipoles, have hydrogen bonding intermolecular forces. And we'll end with another flow chart for determining the type of intermolecular force of attraction. So first question is, are there polar molecules? If the polar molecules are not polar, then the strongest intermolecular force is dispersion forces. If yes, then we ask, are HO or HN or HF bonds present? The reason this is left off is because H and F generally only make one bond, and so it only appears as the molecule HF, not as a part of a molecule. But HO and HN appear as parts of molecules often. So, are these bonds present? If no, but polar, then dipole-dipole are the strongest. If polar and these are present, then hydrogen bonding forces are the strongest. Okay, we will return for some practice exercises and problems in part 2.